Hello everybody and welcome to this A-level chemistry video about the ideal gas equation. This is one of the subtopics in the amount of substance chapter for A-level chemistry. And in this video we'll look briefly at the origin of the ideal gas equation. We'll look in depth at how you use the ideal gas equation, including unit conversions, and then we'll finish by looking at how we can work with gases in equations, including a couple of questions to that effect. The origin of the ideal gas equation can be explained using a simple example of party balloons. If we take a number of identical party balloons with an identical number of molecules of air inside them, we can subject these balloons to different conditions and see how they behave. And their behaviour allows us to come up with some scientific rules that form the ideal gas equation. First of all, if we place a party balloon in a warm environment, say a boiler cupboard, then the party balloons will expand and then they might pop. You can see this same effect if people have put party balloons outside their house for somebody's birthday and it's a hot day, and the balloons will pop. In the same way but the opposite way around, if you took a party balloon and put it inside a freezer, that party balloon would shrivel up. Maybe not go shriveled down to nothing, but it would definitely get smaller. And what this allows us to realise is that the volume of space a gas occupies, the gas inside the balloon, is proportional to the temperature of those gases. So the volume, V, is proportional to the temperature, T. And this is actually known as Charles's law after one of the scientists who did a lot of work in this area. If we took another party balloon and we just simply squeezed it, as we've all done probably when we were younger, we can say that that party balloon, assuming that we're squeezing it and stopping it moving out from between our fingers, that party balloon's actually going to get smaller. And what that means is that the pressure that we exert on gases is influencing the volume, and the pressure is inversely proportional to the volume. What that means is if we increase the pressure, the volume gets smaller. And so this is Boyle's law. Pressure is inversely proportional to the volume. And then last of all, if we were to carefully undo the knot in the balloon and breathe out more air into that balloon, we would find that the balloon, of course, would get larger. The volume would increase. And what that means is we've put more molecules of gas into the balloon, more moles, and so the volume of that balloon is increasing because volume is proportional to the number of moles of gas inside the balloon. And it's these three relationships that we've got here on the slide that combine together to give us the ideal gas equation. And it's called the ideal gas equation because all gases are assumed to behave in this same ideal way, regardless of whether they're carbon dioxide or oxygen or nitrogen. They all obey these rules where their volume is proportional to a number of different factors. So this is the ideal gas equation. PV equals nRT. It's got quite a nice rhythm to it when you say it like that. You need to remember this so you can use it in exam questions because it won't be given to you and you'll get a mark for remembering it. Not only do you need to remember it, you need to be able to understand it and use it, including understanding the units for each of these quantities. So P is pressure, and that's measured in pascals. And pascals is the international symbol, international unit for pressure. V is volume, measured in cubic meters. N stands for the number of moles. T is the temperature, measured in Kelvin, which has got the symbol K. And last of all, R is the gas constant, and it's got a number, 8.31 joules per Kelvin per mole. And you need to remember those numbers, 8.31, because that is a constant, which means that whatever the gas is, it will always have that many joules of energy per Kelvin per mole. So that means if you've got 1 mole of a substance at 20 Kelvin, it will have 8.31 times by 20. That's how much energy that gas will have. Let's move back to the units. Pascals, cubic meters, and kelvins. Probably not units that we use frequently. So let's have a look at each of those now. Let's start with our units by looking at pressure in pascals. In exam questions, they like to try and trip you up by giving you the units in something that is not the SI form, not the standard way of giving it to you. So they might give it to you in kilopascals. And if that's the case, well, that's really lovely, because they might give you a pressure of 3 kilopascals, which, to convert into pascals, you simply multiply by 1,000 in the same way that 3,000 grams is 3 kilograms, or 3 kilograms is 3,000 grams. So that's nice. Atmospheric pressure is taken to be 101 kilopascals. So they might talk to you about atmospheric pressure. That would be a bit mean, expecting you to remember 101 kilopascals. But that is atmospheric pressure, sometimes approximated to 100 kilopascals. So to convert kilopascals into pascals, you just simply multiply by 1,000. Now temperature. Temperature is in Kelvin, and that is an entirely new temperature scale named after a scientist, Lord Kelvin, who did all sorts of crazy experiments in his country house. But essentially, the Kelvin scale is a recalibrated degrees Celsius scale that starts at 0. You might have wondered why we have a temperature scale that goes negative. Wouldn't it be easier if we had one that starts at 0? And that's what the Kelvin scale does. It starts at 0, and that is referred to as absolute 0. That is as cold as it is theoretically possible to get. We've got below 1 Kelvin, I believe, but never down to 0. It's a theoretical temperature. Now, the good news for you and your exams is it's not a really tricky conversion to work between degrees Celsius and Kelvin. 0 degrees Kelvin is minus 273 degrees Celsius. 20 Kelvin is minus 253 degrees Celsius. So you can see that what we're doing is we're adding 273 onto the degrees Celsius scale to get us into our Kelvin scale. So 0 degrees Celsius is 273 Kelvin. 50 Celsius is 323 Kelvin. And so the scale is nice, that's plus 273 or minus 273, depending on which way you're converting. Most likely you'll be adding 273 to convert into Kelvin. But what's really nice is that that increase of 1 degree Celsius from, say, 50 to 51 is the same as 1 Kelvin from 323 to 324. So these first two conversions aren't too bad. Let's take a look at volume. Volume is usually taken to be the trickiest one. Now, the units of volume for the ideal gas equation are in meters cubed, and a cubic meter is actually really quite big. And the reason that we have these big volumes is because gases occupy a lot of space. Now, you can just accept that the volume is in cubic meters, and you can also accept the conversions. So I'll start with the conversions. To convert cubic centimetres, which is quite common to be given a volume in cubic centimetres, into cubic metres, you divide by 1,000,000. And that's because a cubic centimetre is tiny compared to a cubic metre. So a beaker that holds 500 cubic centimetres of volume would actually only be 5 times 10 to the minus 4 cubic metres with the volume. So centimetres cubed to metres cubed, you divide by 1,000,000, and then centimetres cubed to decimetres cubed, you divide by 1,000. The origin of that can be explained using cubes. Here we've got a cube, which I will take to be 1 metre by 1 metre by 1 metre. So that is 1 cubic metre. Now a decimetre is 1/10 of a metre. So this 1 metre dimension here is actually 10 decimetres, and so is this one, and so is this one. So the volume is 10 by 10 by 10, which is 1,000 cubic decimetres. So 1 cubic metre is 1000 cubic decimeters. But we also know that 1 metre is 100 centimetres. So this dimension could also be referred to as 100 centimetres, and this one 100 centimetres, and this one 100 centimetres as well. So the volume in cubic centimetres is 100 times 100 times 100, so a million. And that's the origin of these conversions. cm cubed to metres cubed, we multiply by 10 to the minus 6, or divide by a million. dm cubed into metres cubed, we divide by 1000, and it's the opposite going the other way. So those are the really important conversions to remember. Let's get back to the ideal gas equation itself, PV equals nRT, and let's explore the different forms of this equation, because you might be asked to work out P, and then you need to have an equation where P equals something. So you might prefer to write that equation and then substitute numbers into it and then rearrange numbers. People often find that easier. And so that would be possibly what I recommend. Remember what the units are. And then alternatively, you could use algebra as your method. So PV equals nRT. If I've been asked to work out what P is, I need to divide both sides of this equation by V, and then the V's on the left-hand side cancel out, and we're left with nRT divided by V. And making V the subject of the equation works in the exact same way. However, if we wanted to work out a number of moles, we would need to divide both sides of the equation by RT, and then the RT would cancel on the right-hand side and would be left with PV divided by RT equals N. And so that's the rearranging of the ideal gas equation, either by subbing the numbers in at the beginning or by doing the algebraic method. So let's take a look at a couple of questions here. How many moles are there in 0.050 cubic metres of oxygen gas at a temperature of 450 Kelvin and 60,000 pascals? So the first thing that I recommend you do is you write the ideal gas equation out, PV equals nRT. You rearrange it to make N the subject, N equals PV over RT. And then you write the quantities, V equals, T equals, P equals. And then you do the conversions, because getting into this routine like this encourages you to remember to do the conversions, and if you make a slip up, you're more likely to get method marks when you say use the wrong volume later, that you've shown that you think it's the volume, whereas if you just use the wrong volume later without saying what it is that you're doing, you're less likely to get method marks. So convert each of those quantities like this. Now on this occasion, no conversions are necessary because all of the units are in the correct form, but it's a really good habit to force yourself into. Then plug those numbers into the equation, you get your answer, and don't forget to put the units in. And in this second question, what was the temperature in degrees C of a gas that has got a pressure of 110,000 pascals, 0.4 moles of gas, occupying a volume of 1,600 cubic centimetres. So again, my suggestion is that you write the ideal gas equation, this time with T as the subject, so T equals PV divided by NR. We write down our quantities, and then we take a moment to look at the units. And this time we find out that the volume is not in the SI units that we need, it's in cubic centimetres, so we need to divide that by a million and get the correct number of metres cubed. So dividing 1,600 by a million, we get 1.6 times 10 to the minus 3 cubic metres. And so we plug those numbers into the equation and we get a temperature. Now we should note, I said before, don't forget to put the units. The temperature units are in Kelvin, but this question asked for the temperature in degrees Celsius. So our value in Kelvin, remember, is 273 bigger than our value in degrees C would be. So we need to subtract 273 off this to get our temperature in degrees C. So this is our answer here. Another application of the ideal gas equation is that you can use it to find the MR of a volatile liquid. And to do this, what you have is you have a canister that contains the volatile liquid, and you inject some of it through a syringe into a second chamber. And the second chamber is inside an oven. And volatile means it turns into a gas easily. And so once the liquid has moved into the oven, it will evaporate and become a gas. And so we can measure the volume of gas that is produced in this chamber, and we can take a look at what the mass has dropped by from this canister. So if the canister lost a certain mass, we will know that that canister's mass loss is all to do with the fact that the liquid left through the syringe and into the oven, and then it became a gas whose volume we measured. So let's say that we collected 1,000 cubic centimetres of gas inside the oven, and that the mass of the canister began at 30.0 grams, but then it dropped, and it dropped down to 25.42 grams. And so we can work out what mass has been injected, and that mass is 4.58 grams. And that 4.58 grams of the liquid has got a volume, once vaporised, of 1,000 cubic centimetres. So the first thing that we need to do to work out what the MR is to work out how we're going to calculate the MR at the end. And since moles equals mass over MR, that means that MR is mass over moles. And so the final calculation that we're going to do is mass divided by moles to work out what the MR is. And so that means that the previous step must be to work out what the moles is, because we know what mass has been lost, 4.58 grams, but we don't know the moles. And so we need to use the ideal gas equation to work out the moles. So that's in the form N equals PV divided by RT. We've got our volume of 1,000 centimetres cubed. We need to convert that into metres cubed by dividing by 1,000,000. And we need to take the temperature of the oven, and that is at only 44 degrees C. And so 44 degrees C, we need to convert that into Kelvin by adding 273 onto it. And then the pressure is 101 kilopascals, which we then multiply by 1,000 to get 101,000 pascals. We plug those numbers into the equation, remembering the value for R is 8.31, and we get a value for our moles. We then take this value of moles and we put it into the equation down here, and we divide our 4.58 grams by the moles that we've just calculated, and we get our MR value. You don't normally need to use the units of MR, grams per mole, but I like to put it in because I think it helps give MR more meaning. We're going to finish this video by taking a look at how we can combine the ideal gas equation with other calculations and with other chemical equations. So we've got a situation here where octane, a hydrocarbon with a molecular formula C8H18, burns completely in air to give water and carbon dioxide. Here's the chemical equation for it. Here we can see the numbers in the equation 9, 8, 1 and 1. And then we've been given some data. A sample of octane burns completely in air. The carbon dioxide produced occupies a volume of 20,000 cubic centimetres and has a temperature of 55 degrees C and 101 kilopascals of pressure. And we have to calculate the number of moles of carbon dioxide present. To do this, we need to use the ideal gas equation, PV equals nRT. We're going to rearrange it in the form N equals PV divided by RT. In our data, volume is 20,000 cubic centimetres, which we need to divide by 1,000,000 to get into cubic metres, so 0.020 cubic metres. The temperature is 55 degrees Celsius, which we need to add on 273 to get 328 Kelvin. And last of all, the pressure is 101 kilopascals, and we just simply need to multiply that by 1,000 to get 101,000 pascals of pressure. And then we need to substitute these values into the calculation, and this gives us a final answer of 0.0741 moles of carbon dioxide. And then there's a follow-up question that asks us to calculate the number of moles of octane burnt. And if we look at the chemical equation, the ratio of octane to carbon dioxide is 1 octane for 8 carbon dioxide. And so to convert the moles of carbon dioxide into moles of octane, which is what we need to do, we need to divide it by 8. So our answer from the previous question needs to be divided by 8. And when we do that, we get 9.26 times 10 to the minus 3 moles of octane. And so you can use the coefficients in the equation, those multipliers, to work with moles without having to use moles mass and MR. You just simply use their proportions from the multiples in the equation. Okay, we'll take a look at one last question now. A sample of decane is cracked to produce butane and ethene as shown in the equation below. And we've got decane on the left and we've got butane on the right and 3 moles of ethene. And that's really important, that the decane produces 1 mole of butane and 3 moles of ethene. Now, the reaction is carried out at 550 degrees Celsius, that's T, and 200 kilopascals, so there is P. And our command is, if 11.6 grams of butane are produced, what is the total volume of gas in cubic centimetres? That's so important, let's highlight that. Now, what we need to do first is we need to go PV equals nRT. Our final answer needs to be for the volume, so V equals nRT divided by P, which means that we need to know nRT and P. So N is the number of moles. We actually don't have that yet, so that's going to be something we're going to need to calculate using the mass. R, we know, is 8.31. Might give it to you, they might not. Temperature is 550 degrees Celsius, which is 823 Kelvin. Remember, we need to add 273. P is 200 kilopascals, which is 200,000 pascals. Now, N is the moles of gas, and this is the tricky bit here. We've got 2 gases, we've got ethene and we've got butane. And so what we're going to need to do here is we're going to need to work out the total moles of gas before we need to then work out the total volume of gas. And so we've got the mass of butane, 11.6. So mass divided by MR is moles of butane, and the moles of butane is therefore 11.6 divided by 58, which is the MR of butane, which gives us an answer of 0.2 moles. So this is how many moles of butane we've got. Then we need to look up at the equation, and the ratio is 1 to 3. So if we've got 0.2 moles of butane, we will have 0.6 moles of ethene, because it needs to be 3 times as big. And so therefore the total moles is 0.8. And so this now can be plugged in for our value of N. And so to finish off, we need to calculate 0.8 times by 8.31 times by 823 divided by 200,000, which comes out at 0.0274 cubic metres. And that's not quite our final answer because they asked for it in cubic centimetres, so now we need to multiply that by 1,000,000, and we've got 27,400 cubic centimetres. And so that's the end of this question. We've got our final answer there. This would probably be a 4 or 5 mark question at the very least. Okay, that's the end of this ideal gas equation run through. Hope it was useful. I'll see you next time.